So you touch upon the most important topic of errors. So Quantum Stack provides functionalities for error mitigation, for hardware error optimization, for error correction, and error suppression. These are all different, and can you elaborate on each, particularly emphasizing their distinct roles?
Well, all of those things that you mentioned are components of the big goal of trying to make quantum algorithms run on noisy devices and produce results which are as close as possible to the ideal results. So we want to reproduce the results we would have gotten if the algorithm was run on a noise-free hardware. And all the protocols you mentioned are trying to minimize this detrimental effect of noise, which if it's not handled, it causes the output of the quantum algorithm run on current devices to become meaningless. And this is exactly what we do at Kedma, by the way, my company. We develop all these methods to handle the noise problem. So first of all, the ultimate method, the holy grail, is to perform quantum error correction and fault-tolerant quantum computation. Error correction basically allows quantum computation to maintain its full exponential algorithmic advantage. And the idea in error correction is to take the quantum state of, say, 1 qubit and sort of smear it on many more physical qubits, say 10 or 100 or 1,000, but just keep in mind 10, to get some kind of redundancy. And this is done in such a way that if there was an error in, say, 1 physical qubit out of the 10, the quantum data of the original single qubit can still be recovered by basically making some operation on the remaining 9 physical qubits, which did not suffer an error. And performing error correction, quantum error correction, is the best solution for the noise problem because it has only polynomial overhead. The overhead is not that large and it doesn't scale very badly. So it is a generic solution that works asymptotically for any quantum algorithm, for any algorithm size. It enables basically maintaining the exponential quantum algorithmic advantage that quantum computation promises. This is why all the big companies are working towards that solution. By the way, this is the solution that I worked on in my PhD. But this is a very costly solution. It requires a huge overhead in the number of qubits. So think of 1,000 physical qubits needed per a single qubit in the original algorithm that you want to run, or even more. This is really a huge number. And also, very importantly, for this fault tolerance or quantum error correction, going all the way fault tolerant solution, for this solution to work, the noise needs to be below a certain threshold value. So only when this noise is below that value, the error rate is below that value, when this is the case, quantum error correction actually starts to help. And if it's not, then it actually only ruins things. So unfortunately, getting to commercial use cases with this solution, which is sort of the holy grail, it is really an excellent solution, but it's going to take a long, long time to achieve. I'm not talking about being able to do error correction with a single qubit gate, a single logical qubit, or with a few. This we're either close to or we have already passed this break-even point. But to get to commercial applications, you would need hundreds of logical qubits with thousands of logical gates. Meaning, if you take this 1 to 1,000 rate, this means hundreds of thousands of high-quality qubits. So reaching that point will take at least a decade by the most optimistic estimations, and probably more. Okay, so that's about the solution of fault tolerant and error correction. But the good news is that there are additional methods that can already be applied now on current quantum computers, and they will achieve intermediate but still very interesting results. And these are the other methods you mentioned, like error suppression and error mitigation, and the optimization processes required for these methods to work optimally. So let me talk a little bit about these solutions. So the first very important component in handling the noise is what's called error suppression. So imagine an error which, for example, under-rotates the state of the qubit compared to what the ideal gate should have done, okay? So if you know the exact angle of this under-rotation, you could potentially rotate it back with no overhead at all in time or space. If you know how much you rotated it, you can apply a gate to rotate it back, or maybe correct the next gate to compensate for that. This is what error suppression does. It handles what's called coherent errors, basically rotations in different directions. Q-Control, for example, just launched its software for error suppression on IBM's computers. Unfortunately, though it's extremely important to handle this type of error, there are very important types of error that error suppression cannot handle. And these include perhaps the most problematic type of noise, which is called dissipative noise. So dissipation is what you can think of as loss of quantum coherence. it's the type of noise which makes the quantum information more and more classical. It's as if it's being measured all the time, as if the state collapses. And this type of noise, basically, it injects entropy into the system. It increases its entropy, and it cannot be handled by just rotating back the state. It is much more complicated, and in most systems, this is the type of noise to most worry about. So for this type of noise, dissipative noise, people thought of another approach for handling the errors. So this approach is called error mitigation. Error mitigation is particularly interesting because it manages to correct errors without any overhead in terms of number of qubits. So unlike error correction, it doesn't have any overhead. So in that respect, it is better than error correction. But there's a price to pay, like everywhere. There's no free meal. And instead of qubit overhead, what we have to pay is overhead in time. So the idea is that instead of running the quantum circuit once on the noisy device, the error mitigation protocol runs several quantum circuits and then post-processes all the outcomes of these circuits into one result, highly accurate result. And this way, the error mitigation recovers the ideal behavior of the algorithm with high accuracy. But the point is that despite the dissipation, the final output is as accurate as if the quantum algorithm was run on a noise-free quantum device. The only thing is that you have this overhead. So this solution eliminates the effect of errors. There's in fact many actually methods to do this, PC, ZNE, and more. But then we have to go back to this small problem of the time overhead. And there's a proof that actually this time overhead for error mitigation necessarily grows exponentially with the size of the algorithm. And so there's a problem here, and you have to minimize the overhead in time. So the different methods of error mitigation differ by several things. They differ, first of all, how general they are, and then how accurate they are, and whether they eliminate biases caused by the noise or not, and of course, how time efficient they are. And the nice thing is that you can make the delay in time worthwhile, even though the delay in time is exponential, provably, as I said before. You still can make it sufficiently small so that you don't lose too much of the huge potential exponential advantage of quantum algorithms. So for example, at KEDMA, using error mitigation combined with error suppression, we managed to increase the sizes of the quantum circuits that we can run on noisy devices by a factor of 100 or even 1,000 in terms of the circuit volume compared to the noisy case. Okay, so this is a really huge factor. And it can take you a long way. So these will be circuit volumes, which in no way you can run without handling the noise. And these factors in circuit volume of 100 or 1,000, it will only increase in the future to larger factors. Since the reason it will increase is that with time, end users will want more and more accurate outcomes. And it turns out that the advantage that error mitigation gives over the noisy case, this factor only grows with this accuracy. As the required accuracy gets better, this advantage of error mitigation over the noisy case only becomes larger. So all these methods are the methods that you mentioned for handling noise. And as you see, they sort of address these noise problems in different ways. And all of them require a huge amount of optimization to make them work optimally and to minimize the cost. And I should mention there are quite a few companies already working on these solutions. KEDMA, for example, specializes in this. And of course, IBM and Quantinuum and IonQ and all the big companies are developing their own approaches.
Okay, great. Thank you for your overview and highlighting the strengths and limitations of each of the methods.